Section 10.1 is on page 673, talks about graphs and graph models. So we start with the definition of a graph G between two vertices V and E consists of non-empty sets of vertices or nodes. That's what we're going to call them. As we do this example, you'll get accustomed to this kind of notation. And V, a set of edges. So these are the nodes or the vertices, what we're going to call them later, and these are going to be the edges. Vertices, edges. Each edge has either one or two vertices associated with it. Here you'll notice San Francisco has two, Los Angeles has two, but in later on graphs, when we glance, we will notice that some of these have one. Let me find one. There. Chen only has one, Camino only has one, so you know, that could be the case. An edge is said to connect two endpoints. So each edge must connect to endpoints. If there's only one endpoint and no edge between another, then it's just a point. Let me see if I could find one too. I know there's one in the examples. Let me find one. Right there, E. E has a vertex or a node, but it doesn't have any edges connected to it. So if you connect an edge, you'll notice now it's connecting 1, 2. If there's none, you just leave it alone, just as is. Again, not to worry about this, we're going to go over those. Let's define a few things. You need to memorize what each type of a graph look like, but there are only 4 types that you gotta worry about, or get accustomed to. Not memorize the definition, but understand it. Remark: the set of vertices V to a graph G may be infinite. A graph with an infinite vertex set or an infinite number of edges is called an infinite graph, and in comparison, a graph with a finite vertex set and a finite edge is called a finite graph. We're going to deal with finite for the most part. In this book, we will usually consider only finite graphs. So, a computer graph generates the following: a connection between San Francisco and LA, San Francisco and Denver, Los Angeles and Denver. From Denver, it only connects to Chicago. So, you go to Chicago, you go San Francisco or Los Angeles. It doesn't specify any direction. So, first definition we have, actually the first definition we defined up there, but let's talk about defining a graph. A graph in which each edge connects two different vertices and where no two edges connect the same pair of vertices is called a simple graph. Okay, so that's what a simple graph is. The graphs that have multiple edges connecting the same vertex are called multi-graphs. So those you gotta just remember how this works. Kind of like not memorize this word for word, understand it because they're gonna ask for that. Here's one. Now, if you look at the diagram we have up there, that's a computer network. Now, if you look at a computer network with multiple links, you'll notice Denver has multiple, Chicago has multiple, right? Not just a single line connecting them. There's Denver to Chicago, there's a connection. We don't know what it was, but now we know there are 3 connections. And if we add direction later on, then it becomes more evident how things work. Kind of like a one-way street or a two-way street. We know there's a street connecting 2 blocks, but which way can you go? We'll get to that in a minute. A loop is an edge that connects a vertex to itself. So that's kind of like driving on a freeway and taking an exit to stay within the city, or if you're exiting a freeway. If you are in the airport, this happens a lot. You'll notice that you missed the gate that you want. They say they have an exit that says return to airport. You just loop back. So if you're on a website, that would be something like when you reload the page. It's slow. You click reload. That's really directing the page back to itself. Graphs that may include loops. So simple graphs can't have loops. Graphs that may include loops and possibly multiple edges connecting the same pair of vertices or vertex to itself are sometimes called, I can't pronounce that word, I think it's pseudographs. I could be mistaken. I was going to Google it, but I forgot. So here, something like that. Now you could loop back, you could go from one city to the next, and so on and so forth. And now we talk about the second category that we're going to deal with, which is a directed graph. What are directed graphs? Consist of the same as before. V is non-empty set of vertices, edges or arcs, as you notice. That's an arc, that's an edge. Each directed edge is associated with an ordered pair of vertices. The directed edge associated with the pair where you start with U and end with V. Now, if you look at that's directed specifically from Denver to Los Angeles. So you notice, if I want to read this, San Francisco, you could only go out. It seems you can't get back to San Francisco in this specific network. And that's very important. That's like a one-way street. So you need to figure out how things work. So it seems in Denver, I could go back and forth between them and LA, but I can only go from San Francisco to Denver. I can't go back from Denver to LA because there's no direction back. And that turns out to be extremely important for multiple applications. I don't need to tell you how that works. This is a computer network. That's more of how this looks identically. So if you want to put those, and now you're adding those two ways or multiple ways, or you're adding extra directions, that's how it would look. And this specifies how often these things happen. So notice here, this is only directed out of San Francisco, so you can't go back. But now this tells you you could go back and forward. And we have other types of graphs. I only put them there so you could see them, kind of see how these works. Depending on what you're doing, you don't have to learn the type of names, It's not like, oh, hey, what is that Equinchip? You don't need to know that. Influence, a graph. If you look at this and you want to read it, the direction tells you who influenced what. It seems Linda's being influenced by two people only, Deborah and Brian. And it seems Fred is being influenced by Deborah and Yvonne, but can influence Brian. And you can get the idea of how this works. So you could use that to figure out who influences who. That could be a structure of friendship. That could be an influence of a workplace, manager, supervisor, all these different things. Here things get a bit messier. I'm going to do one of those for you. A call graph. That's what computers do. They track all of these things. I mean, computers could do this much easier than we do. And you'll notice the first. So you could omit the first number since they are the same and just go by the last 4 digits of who's calling who, how many calls. That's what they do on your phone and so on and so forth to figure out, if before we were charged for calls, so let's say those are international calls. So to figure out who's going to be charged for what, people that call, I'm overseas in Lebanon right now, and if I receive a call, I don't pay. The caller pay in Lebanon. That's how the system is. But in the US, you get charged regardless whether you're calling somebody or somebody's calling you. So, different systems. And this is another call graph, but this is just kind of like showing the main goes to what, to display, to protocol, and how it works. Main runs to everything. Nothing runs back to main. Kind of like a CEO gives their commands, and everybody beneath them has to go and filter down to managers, supervisors, cashiers, so on and so forth. The right is a program. How that's how you set those. You could deal with the programming part. I'm not including that because I'm not sure how many of you have taken programming, but I'd love to show you one of those or write a program for you, but that takes a long time. And here it talks about, the rich overlap graph. This is something we're going to come back to in one of the examples. That's why I'm pointing that out. So you'll notice the connection here is between, for example, a mouse has only one connection. It can only connect back and forth to that one, no other squirrel has 4 connections, and so on and so forth. And this is protein interaction graph again, if you're interested in those. And here they talk about nouns. I took those out of the homework because I'm not sure how comfortable you are with that. So there, I'm just showing you, you could do so many different kinds of, and you don't have to do all of these diagrams, but you have to do some of them on the homework, and that's what you're going to have to reproduce on the exam. These are networks of, like competitions. One of them is single and remaining tournament. And here, this is a graph we're going to come to, and we're going to pick out how this works. Again, how this plays, who beats who, or who influences who, kind of the same idea. So we're going to start with an example. Now, table 1 is in the book, but you don't have to refer to it, really. You could just figure out how things work between whether there's an edge or not. So they say, what kind of graphs from table 1 can be used to model a highway system between major cities where A, there is an edge between the vertices representing the cities if there is an intersecting highway between them. Well, here we would say this would be a simple graph. Again, you don't need to refer to the table. Kind of glance at this and figure out how this works. There might be more than one answer, but in general, we're going to pick those. I shouldn't use the word simple, but straightforward, so they don't overlap. B, there is an edge between the vertices representing cities for each interstate highway between them. This would be a multi-graph. So intersection between 2 pairs of cities, that's why. And C, there is an edge between the vertices representing cities for each interstate highway between them, and there's a loop. They allow the loop at the vertex representing a city if there is an interstate or highway that circles this city. Oh, excuse me. And this will be again, I'm not sure if I'm pronouncing that right, but there it is. Now that stuff is no fun. This is more fun. So when you look at these networks, it says, well, here, determine whether the graph has directed or undirected. And we notice that we have undirected, and I know they're asking for more. This one is definitely directed. You see that direction right there. What else? It has multi-edge, and whether it has one or more loops. I mean, you could see those clearly, the loop part, but let's talk about multi-edge. If I want to go for multi-edge, well, of course, multi-edge, and no loops. And this one has no loops as well. I should have used different colors, but it's okay. And this have multi-edge, or multiple edges, same thing. Here we have loops, of course, you can tell, hopefully, and multi-edge graph, again. It says, for each undirected graph in 3 through 9 that is not simple, find a set of edges to remove to make it simple. Well, I forgot to get those. Let me cut those and put them here. For each undirected graph in 3 through 9 that is not simple, find a set of edges to remove to make it simple. Well, this is simple already, so no need to worry about that because it satisfies those conditions. In number 4, if we take that, and if we take any two of those, let's say those two, again, it doesn't have to be, any two will do. That becomes simple. If I get to number 5, if I remove all 3 loops and one of those, and one of those, again, any one of these edges will do. It doesn't have to be specifically, so it doesn't have to be the bottom. I'm just choosing those at random. Now it becomes simple. And if I look at number 6, all what I have to do is remove, again, any one of those or any one of those. That becomes simple as well. Now, okay, pause for a minute. 7 through 9, I didn't really talk about this because they're directed graph, and they're directed graph, they can't be made simple, and there's no fix in them. So removing an edge or a loop does not fix that. Here it says use the niche overlap graph figure in figure 11 to determine species that compete with hawks. Again, you don't need to really know what they're doing exactly, but you do recognize where a hawk is, so you could tell hawk competes with owls, obviously, with raccoons and crows. And that's pretty much it. Raccoons, owls, and crows. On number 16, draw an acquaintanceship graph. Again, you don't need to really memorize what these mean. They're just specific graphs that are best fit for certain type of applications. That represents that Tom and Patricia, well, let's see, Tom and Patricia, okay, T and P, T and H, T and S, T and A. So it seems Tom is connected to everybody. Okay, and let's see. M, let's hope the letters, oh, there is Marique and Mary. So we'll write the names, I suppose. So Tom connects to everybody. He's going to be in the center. Tom and Marika, Jeff, and P, Jeff, and M. P and H. Okay, so those are dwellings. So if I put them in pairs, kind of to see how this works. T for Tom, Tom and Patricia, Tom and Hope, Tom and Sandy, Tom and Amy, Tom and Marika. Okay. Oh, and there was Tom and an M before, no? T and P, T and H, T and S, T and M, T and Mary. Jeff and Patricia, Jeff and Mary. Then there is Patricia and Hope, Amy and Hope, Amy and Marika know each other, but none of the other pairs know each other. So it seems the main center should be on Tom. Let's say Tom's in the center. And from Tom, I could do this so many different ways. Tom could go to Amy. Now let me see. What does Amy? Amy has 2 other connections. So those 2 are the same, but this is the most. So let's say Amy's right there. This is Tom. And H and M. Let's say H is right here. And Hope is right there. So if I do this right, there's a connection between those 2. Tom is also connected. Okay, and the others. Tom is connected to Patricia, right? Yeah. So Tom to Amy, Tom to Patricia, Tom to Hope, Tom to Sandy, There you go. Now Patricia is connected to Hope. Tom's connected to Patricia. We got that already. And Tom's connected to Mary. No, Marika. Marika. We did that right there. Okay. That's, what is that? Oh, that's J, not T. Okay. That's it. So did I do that right? But Tom is also corrected to B. Okay, so J is Jeff. Let's say Jeff is right there. Well, actually, yeah, right there. I was gonna put him then down. Jeff is connected to Patricia, and Jeff is connected to Mary. A and H. A would be Amy and Hope. And A and Marika, Amy and Marika. There we go. I should have used different colors for those. Okay, you could also make it a square if you want, you know, different things, but this is one that seems to work nice. How about here? 18. If I was to ask, who can influence Fred? Where's Fred? Fred right there. Fred can be influenced by Deborah and Yvonne. And Fred, okay, let's see. Who can influence Fred? And who can Fred influence? Fred can only influence Brian. That's it. Okay, good. So, you know, they're very useful. Here it says, this looks very complex, but when they say, which other teams did Team 4 beat? Team 4 beat, let's see who beat. And which teams beat 4? Where's 4? A bit lower. Here we go. 4 was able to beat 3. Team 4 can beat 3. And it seems that's it. Which team can beat 4? Well, teams that can beat 4 are, yeah, it seems 4 is getting their butt kicked by a lot of teams. Let's see. 5. I'll put them here. 5, 6, 1, and 2. You could put those in any order, of course. But that's what it seems